Hello class, this is the video for section 5.2 and here we talk about definite integra, and these are our learning objectives. At the end, you should be able to define what a definite integra is in terms of Riemann sum or sums, use the sums to evaluate integrals, and then understand the properties of what integrals. Okay, now here is the definition that if a function f of x, f, is defined over a closed interval a and b, and then we divide the interval into sub n intervals, or say rectangles, to estimate the area under the curve. And then we have defined delta as x as what? B minus a divided by n. Okay, where your x0 is the left end point of the interval, and the x1, x2 up toward xn, which is we call to the b. And these are the endpoints, okay, of these were sub-intervals. And we're going to denote the x, x star I as what? A sample what point, or sample points. And this could be the left end points, the right end points, or the midpoints. Okay, in this section we're going to denote a different variable for midpoints, and I'll show you in a minute. Okay, so if you have that, then we say that the definite integral, which will always give us a number because we evaluate the area and get a number, is defined as what? The sign, the integral sign from a to b. Remember, the elements of the function is defined over those what values, or the closed interval of f of x with respect to x is the same as what? The limit as n goes to infinity of what? The sum of what? F of x star I times what? Delta what? X. Now remember, this part of sum is what we did in 5.1, where we talked about the what? The area of what? The rectangles that under the what? The curve. Now this is true provided what? The limit exists, and it gives the same value for all choices of what? The sample points. For all choices, this could be the left end, it could be what? Right end, or it could be the midpoint. Okay, now if this, okay, does exist, then we say that f was integrable on the interval a and b. Okay, there are about 5 notes or remarks that we want to make. The symbol, okay, is introduced by Leibniz and is called the integral sign. Okay, it is an elongated what? S, if you want to call it. If you stretch the S, you get that symbol. That's the integral sign. And because an integral is a limit of what? It's a limit of sums. Okay, now the notation, the integral of the limits a to b of f of x with respect to ds is called the what? It's called the integrand. The f of x is called the what? The integrand. And then your a and b are what? The limits of what? Integration. And here we call the a is what? The lower limit. B is the what? The upper limit. So for now, the symbol dx has no meaning but by itself. Okay, so when you consider this, is all one word, one symbol. Okay, the dx simply indicates that the independent variable is what? Is x. In other words, we integrate with respect to what? The value, the variable x. And the procedure is what we call what? The integration. Okay, now remember, integration, basically we find the what? We'll be good to know that we find the antiderivatives of what? The antiderivatives of the differentiation. Okay, so if you are talking about the rates, can talk about rates of change, which is for differentiation. If you're going back, we are what? We are, if you accelerate, you decelerate. Okay, if you have, there's a word like div velocity, then means you go backwards of what velocity to get the displacement. All right. Now the note or remark number 2 is this. This is the definite integral, and it's always a number. It does not depend on what? It depends on x. In fact, if we have this, okay, if I have this place with x without changing the value of what? The integral, it is always going to be what? This is always going to be what? A number. It is always going to be a number. And this sum is what we call the what? The Riemann what? Riemann sum. And therefore, if you talk about it in this integration, okay, if you take the limits of the Riemann sum and goes to infinity, this is equal to what? A definite integral with the lower limit a, upper limit is what? B of f of x with respect to what? X. And what does this give us? They give us what? The area, sorry, the area under what? Under the curve f of x. Okay, this Riemann man is a German mathematician and who lived from 1926 to 1966, for 40 years. And he made a great contribution to integration or calculus. All right, so if the function f has both positive and negative values, as we can see in this figure, okay, then the Riemann sum will have what will be positive if of the rectangles above x-axis and is negative below the x-axis. And then if you add all this together, we call it what? The net area. And it's also called the difference of what? Of sum. So we're going to have, so if this is 2 and this is say -1 and this is say another 2, then the net area in this case, okay, if we know, I'm making this up, this will be what? 2 plus what? 2 minus 1. That is going to be what? That's going to be 3. Okay. So remember, this is what? It's an approximation of what? Of the area. Unless the n is what? Is infinitely, and then that becomes exactly the what? The actual area under the curve. Okay, the note number 3. If you consider a situation where, remember, for using the Riemann sum, we said that each rectangle has equal width, all right, which is given by what? It was given by what? Delta x, and that is what? B minus a over what? Over a. That's the number of what? Subintervals or rectangles. Now, assuming if we have unequal what? Width, okay, this is one advantages. Okay, the advantage is to work with what subinterval with this. For example, in exercise 5.1, in section 5.1, this NASA provided velocity of data, okay, at times that were not equally what? Spaced out. Okay, now we're going to see example in the next slide. Okay, the table below provided by what NASA give the velocity data for the shadow, okay, between liftoff and the what? The jettioning of the solid rocket boosters. Estimate the height above the Earth's surface of the Endeavour 62 seconds after what? After liftoff. So they launch 0 and the velocity is 0. And when they launch, within the first 10 seconds, all right, this is the velocity of the rocket or and then 15 seconds, that is it all the way through. So we should estimate the height of the what? Or the height above the what? The Earth surface. Okay, what are our subintervals here? Okay, the subintervals here, okay, are what? 0 and 10. It said up to 62 seconds. So we're going to go from 10 to 15 seconds. And then we have what? 15 to 20. And then we have 20 seconds to 30 what? 32. And we have 32 to 59. And then we have for 59 to 62. So you can see that these don't have what? Equal. These are what? Unequal what? Time intervals. Okay, or we can say they have unequal what width. Okay, so what is the distance above the what? The Earth's surface. Okay, now we're going to denote that distance d, and we will use the upper what? The upper end, the upper endpoints or the right endpoints. All right, so for this interval, the first interval, okay, we use the velocities. Okay, this gives the what? Let's say use velocities. Okay, use the velocities at right what? Endpoints. Okay, so we're going to denote that distance, and this is going to be from, okay, how many of them? How many subintervals? Well, 1, 2, 3, 4, 5, 6. So we're going to get from one subinterval to what? To 6 of what? The velocity vi delta what? Delta what? Delta t, the ti. Now remember, this is not just delta t, because each t time difference will be different. Because the first subinterval is 10, this is 5, this is 5, this is what? 12, and so on and so forth. Okay, so if you want to use that with the upper limit, you have the velocity at 10, so this will be what? 185, okay? 185 times the time elapsed is what? Is 10. The second is what? 319 times the time elapsed, which is 5, plus the next one is what? 447 times the time elapsed, that is going to be what? That's also 5. Then we have for 740, that's the velocity, 742 times the time elapsed is what? Is 12. Then plus up to 30, we have 3. Then this will be 3,325. Okay, the time elapsed is what? It's actually 27. And then finally we have 1445. That's a velocity at what? 62 seconds times the time elapsed, which is just what? Which is just 3. Now when you evaluate this, this is equal to what? 54, okay? 694 feet. That's the distance, okay? So you can see that this definition that we have with the Raymer sign, it allows us to even what? Solve a situation where we don't have what? Equal time intervals or equal what? Sub intervals. Okay, all right. So that takes us to the next remark, which is number 5. Okay, now I said that we can define the definite integral for an integrable function, but not all functions are integrable. Okay, the following theorem shows that the most commonly occurring functions are in fact integrable. Okay, but this theorem is proved in advanced class, not in this class. So the theorem says that if f is continuous and defined over the interval a and b, or if has only a finite number of jumps, discontinuity, then f is integrable. And that is the definite integral that exists. So if f is integrable on the interval a and b, the closed interval, then the limits in the definition 2 exist and gives the same value no matter the choice of what? The sample points. And remember, the sample points in this case, this we said this could be what? The left end points, the right end points, or the what? The midpoints. All right. Now, let's go to another theorem where we use the Raymer sum, okay, and then write the integral as a Raymer sum or a Raymer sum as what? As integral. So we say that f is a function f is integrable on this interval. Then the definite integral with lower limit a, upper limit b, with the integrand f of x is equal to the limit as n goes to what? Infinity of the what? Of the function f xi times what? Delta x, where we assume that the this delta, the sub-intervals, they have what? The rectangles have equal what? Width. Okay, now we have already defined this. And then your xi is equal to the a plus what? I times what? Delta x. So that you can get the xyi, x1, x2, x3, and then plug it into the function. Okay, so here's an example. Say express the following, okay, as a definite what? Integral. So according to this theorem, we are looking at from the right-hand side, we're going to what? From the right to the left. Okay, we want to write the sum given, we want to write as what? As a definite integral. Okay, so what is that? Now let's go to this. Now, what do you think would be my lower limit of the integral, and what would be my upper limit of that? Okay, so here, what we have here is that my a is what? 0, my b is what? 1. So if you write as a definite integral, it will be integral from a to b, okay, and then it's what? F of xi, all right, times dx. Okay, so if you specify the value, this will be from 0 to what? Okay, 0 to that. What's my f of x? Okay, this is f of x, not fxi. It's f of x, and that is here my f of x is what? E raised to x divided by 1 plus what? 1 plus x. So we're going to put the e to the x over 1 plus x with respect to what is. That's all. Okay, the second one, exercise number 18. Here, your a is what? 2. Your b is 5. Okay, and then your f of x is going to be x times the square root of 1 minus what? X cubed. So this is the integral from what? 2 to 5. Okay, my f of x is x times the square root of 1 minus x cubed. And then we integrate this with respect to what? With respect to x. Okay, so that is all we need to do. Now, going the other way, okay, going the other way, that is, if you have this and want to write it in this and then evaluate, it's a whole lot of work. Remember in 5.1, I did an example where we just have to write it as what Rimasan, and we said we'll evaluate it when we get to section what? 5.2. So we'll take an example, but before that, let's look at this exercise. It said the table of values of n of an increasing function f is shown below. Okay, use the table to find the lower and then upper what? Estimates. Use the table to find the lower and upper what? Estimates of this integral. Okay, so we have for the integral from 0 to what? 30. Okay, f of x with respect to what? X. So it said f is what? Is increasing. F is increasing. Now, if x is increasing, now it means that, remember, if you have an increasing function, the left end point, what does it do? It what? Lower estimates. So we have ln, this one lower estimates, okay? And then the right end point, what? Upper estimates. The what? The area. Okay, so if I want to look at the lower estimate for this function, then I have to use what? The L what? The Ln. So the question is, what is my n? Okay, and what is my what? Delta what? Delta x. Well, how many subintervals we have there? Okay, they have the subintervals from what? We have 10 to 14, that is 1. We have 14 to 18. we have 18 to 22, okay? And we have what? 22 to 26, and then we have what? 26 to 30. So how many are there? How many are your n is what? It's 1, 2, 3, 4, 5. So n is what? 5. So then what is your delta x? It is what? B minus a divided by what? Divided by n. So in this case, it will be 30 minus 0 divided by 5, which is equal to, sorry, it's 10. Yeah, it is, because that's from 10 to 30 divided by 5. That will give me what? That will give me 4. Okay, so if that is the case, then I want to find what L4. Okay, L4 in this case is given by, okay, if you write the whole function, you have the integral from 0, sorry, 10, it's not 0, as 10, that's why I was writing that, it's 10 to 30 of f of x dx is equal to the limit, okay, so it just is approximately, this is, we're not going to take the limit now, approximately we have 1 to I equal to 10 to 30, okay, and then you have f of xi times delta what? Delta x, okay, so we have delta x is what? Is 4, so we want to find L4. So this is approximately, to find the lower limit, is going to be, we are taking the f at what? We have to find the f of x at 10 plus f of x at what? 14 plus f of x at 18 plus f of x at 22 plus f of x at 26, all times delta x. So when you evaluate it, this is going to be minus 12, minus 6, minus 2, and then plus 1, plus 3, all times what? Times 4, and that will give us minus 60 or 68. And then if you do the R5, okay, this is that's R4. 1, 2, sorry, did that? It's 5, not 4. R4, 5. Okay, this is also, yeah, it's summing from what? From 10 to what? 30 of f of x, f of xi times delta x. Okay, what would that give us? We are using the upper limits this time. So it's going to be this times f of 14 plus f of 18 plus f of 22 plus f of 26 plus f of 430, then everything times delta what? X. So that is going to be negative 6, okay, minus 2 plus 1 plus 3 plus 8 times 4. And that will give us positive 16. Okay. All right. So we say that this is what? This what? Lower estimates. These are lower estimate. And that is what? Upper estimates. Okay, upper estimate. All right. Okay. Now, we are going to use this, but the example, I'll do that in class because the example, it takes a lot of time. I don't want to rush through. And then secondly, it takes about, when I did it, it took more than 1.5 pages. Okay. Now, remember when you add the first positive n integers, okay, is given by this, the sum of that, or the square, and then the cube. Okay, we know this from 5.1. All right. And then also, if you have a constant, you add a constant n a couple of times, it's just what? N times c. Now, if you have a constant finds, when the constant doesn't depend on what? The I, then you can break it outside the sum. That is one property that we use. And then we also have the sum and then the difference. So we have the sum and then what? The difference. Okay, so we have this, properties that will apply to solve this problem. But like I said, I'm going to do this in class. I'll do this in class. Okay, here I'll try and set it up. All right. Now, first, this is the function f of x. Okay. My f of x is what? X squared minus 4x plus what? Plus 2. So I can write this as what? The integral from a to b of f of x what? Dx. Okay, where your a is 1, your b is what? Is 4. Okay, now we know that the delta x is actually given by what? Is b minus a over what? Over n. And so if I do this, this is 4 minus 1 over n, and that is equal to what? 3 over n. So I'm going to express, the question is that we said that this is equal, according to Riemann sum, is the limit n goes to what? N goes to infinity of what? You have from a to b, okay, of f of xi times what? Delta x. So the question is that what is the xi? Xi is what? A plus the I times delta x. Okay. So if I do that, what's my A? My A is 1. So there's 1 plus I times delta x, which is 3 over what? Over n. Okay. So that is simply equal to 1 plus what? 3I over what? Over n. So it means that if I have this function, this integral from 1 to 4 of what? X squared, okay, minus 4x plus 2 dx, right? I want to express this as in terms of a Riemann sum, or the limit of the Riemann sum, right? The limit of Riemann sum of this expression, f of xi, okay, times what? Delta x. Now this is your b. That's why this is supposed to be 4 and then what? And 1. Well, like I said, I'm going to finish up this solution in the what do you call it? Actually, it's not to be up to n, because you have to add it. This is from 1 to what? 1 to n. Okay, here is n from a to what? To n, or a equal to 1. I equal to 1. So we have I equal to what? Equal to 1. So therefore, if I want to do this, that means that I need to, since I have my xi, right, then I have to express everything in that form. So this will be the limit n goes to infinity of the sum from 1 to n, or I equal to 1 to n. And then I have what? Xi squared, because the function is the x squared minus, and then minus 4xi, then plus what? Plus 2 times delta x, which is what? 3 over what? N. And then we'll express everything in terms of n, and then what? And then evaluate it. So we can look at xi squared, which in this case will be 1 plus 3i over n, and then we'll square that. We'll simplify that. And if I have what? 4xi, that is going to be 4 times 1 plus 3i over n. And then the 2 also come. So we'll complete this in class, okay? I just want to set it up here, complete in class. Okay, thank you. Now, here is the midpoint. Remember, the x star I represents what? Any sample point. Now, if I'm using the midpoint rule, then we're going to denote, give a different name. In this 5.1, I said this is a midpoint, but in 5.2, the midpoint is given by what? X bar I. This is your what? The midpoint. Okay. All right. So if you have this, this is the definition. that says that for the midpoint, if we use a midpoint, remember we don't need to take the limit. Okay, if you take the midpoint, you don't need to, because midpoint is a better approximation. So any Riemann sum is an approximation to an integral. But if we use the midpoints, we get the following word approximation. It is very accurate. We don't need to find what any limit at all. Okay, so the same definite integral is approximately, okay, it's approximately equal to what? The sum from I equal to 1 to what? N of for f of x bar I times delta what? Delta x. Okay, where your x bar is what? The average of the average of each one sub-interval. Okay, delta x is the same. All right, so here I'll use it to solve one problem, and then we will end this section. Okay, so it's a use the midpoint rule to evaluate the integral with a given n. My n is 4, and I have this what? Integral. All right, so the integral from 0 to what? To 8 sine of or square root of x dx is approximately, see that I don't take the limit of that, it's approximately the limit. What is n? N is what? N is 4. Okay, f of what? X bar times what? Delta what? X. So we need to find what is delta x. What is delta x? Delta x is always what? B minus a over what? N. So in this case, it's what? 8 minus 0 over 4. Because here, your a is 0, your b is what? Is 8. So this is equal to what? Is equal to 2. All right, so what are my sub-intervals? The sub-intervals. Okay, so from what? 1 to what do you call it? 0 to 8. Okay, this is where we have that. So this would be what? 0 and 2. 2 to what? 2 to 4, because each width is what? Is 2. Then 4 to 6. And then what? 6 to what? 6 to 8. Now you see that how many are there? That's what? N equal to the 4. All right. So then the integral from 0 to what? 8 of the sine of square root of x with respect to x is approximately equal to, okay. Now let's find the midpoints. This will be, this is 1 is the midpoint of the 2. The first one, this is 2 plus 0 over what? 2, which is 1. Okay, x bar 2 is a second subinterval. So 4 plus 2 over what? Over 2, which is 3. Then x bar 3 for the third was subinterval. That's 4 plus 6 over 2 is what? Is 5. And then x bar 4. X bar 4 is what? It's going to be what? It's going to be 7. So then this is the sum I from 1 to what? 4 of f of 4 xi times delta x. So that is equal to f of what? X bar, this is a bar, f bar 1 plus f of x bar 2 plus f of x bar 3, then plus f of x bar 4. Now everything times delta what? Delta x. Okay, this is, that's where we got that's f of 1 plus f of 3 plus f of 5 plus f of 7. Everything times delta, which is what? Which is 2. So let's evaluate that. This is what they have, the 2 outside. Okay, this is the sine of square root of 1 plus the sine of square root of 3 plus the sine of square root of 5 plus the sine of square root of 7. every time times 2. So when we evaluate this, this is equal to, use a calculator, you have 6.1820. And that will be my answer. Okay, so now let's talk about those properties, okay? Properties of integration. Okay, we are given this, we're going to use this a lot, all right? So if you find if you have an integral, definite integral with the limits a to b, if you switch the what, the limits of integration, you put a negative in front of that, okay? Then if you integrate from the same limits, a and b, the lower and upper limits are equal, then this is going to be what? It's going to be 0. And then if you integrate a constant, it's just going to be the constant times the difference between the lower and upper limits. Okay, if you have the sum, then you can distribute the what? The integral sign over what? The sum, and write it like that. Okay, if you have a constant times that, you can bring the constant out and write like that. So for example, if I have like 2 times x squared dx, I can write this as what? Let's say from 1 to 2. Okay, I can write this as what? 2 times what? 1 to 2 of x squared dx. Okay, here if you have something like from 0 to 0 of x squared dx, the answer will be 0. Now over here, if you have something like 2 to 3 of, say, x squared dx, this is the same as minus integral from 3 to 2 of x squared dx. Okay, and then of course if you have the difference, you can also write it like that. All right, so that is the end of this section. We'll get to section 5.3 next. Thank you.